Hello everyone, my name is Rahmadi Trimananda. Today I'm presenting to you our work titled Understanding and Automatically Detecting Conflicting Interactions Between Smart Home IoT Applications. This is joint work between myself, Seyed Amir Aqajari, Jason Chuang, and Brian Demsky from UC Irvine, Harry Shi from UCLA, and Shan from the University of Chicago. In this work, we focus on the interaction between smart home apps. Modern smart home environments allow the users to write and install apps to control smart home devices and perform certain tasks. Let's take a look at this example. Let us suppose that we have app 1, fire CO2 alarm. The task performed by this app is turn on the alarm and unlock the front door when the sensor detects that there's a fire. Let's also suppose that we have another app, app 2, lock it when I leave. The task performed by app 2 is lock the front door when the sensor detects that someone is leaving the house. Let's imagine that a homeowner decided to install both apps. While the fire CO2 alarm app potentially unlocks the door, the lock it when I leave app potentially locks the door. Let's imagine that the house was under a fire and there were 5 people inside the house. Upon detecting that there's a fire, the fire CO2 alarm app would unlock the front door, and let's suppose that one person was leaving the house. At that moment, the lock it when I leave app would lock the front door again while the other 4 people were still inside the burning home. So, should the door be locked or unlocked? Since we have multiple apps with different expectations, we have a conflict. These apps run on a smart home environment that can integrate different smart home devices, such as a door lock and an alarm. In this work, we investigate the Samsung SmartThings environment. App 1, App 2, and potentially other apps can be installed and run on the SmartThings cloud. They can write to or read from global variables that represent system states, and the apps control the devices through device handlers or device drivers in a more generic term. In our example, the fire CO2 alarm and lock it when I leave apps use the alarm and the door lock device handlers. Here is some of the state-of-the-art related work in smart home apps that you can find in more detail in our paper. To this end, we did not find any wide-scale study on smart home app interactions. In our work, we first attempt to perform a wide-scale study to understand smart home app interactions thoroughly. Then we use the insights we gain from the study to build an effective tool for conflict detection. Now I will present to you our study on app interaction. In our work, we found that we can observe app interactions in the smallest group, namely a pair of apps. We defined 5 research questions to guide the study. Then we use the insights we gained from the study to build an automated detection tool. Finally, I will conclude this presentation, and now let's look closer into our work. In this work, we first conducted a wide-scale manual study to better understand app interactions, namely the interaction patterns and problems. Our corpus consists of 267 apps from both official and third-party sources. Compared to recent studies on smart home apps, we have among the largest app suite. We manually examine these apps in pairs. In order for apps to interact, they have to be in a group. We discovered that app interactions can be observed in the smallest group, namely a pair of apps. We did not see any patterns in the code for which the addition of another app would exhibit new behaviors that could potentially change the interaction patterns between apps. Therefore, we can decompose multi-app interactions into pairwise interactions. There are 3 ways that apps can interact, so we examine pairs for each of these interaction mechanisms. First, we can pair apps that control the same device. We collect all such pairs in a group called the device group. For example, a pair of apps that control the door lock. Second, we can pair apps that interact through the same medium. We collect all such pairs in a group called the physical medium group. Apps in a pair interact through one of the 4 mediums: motion, light, water, and sound. For example, we can pair app 1 that turns on a light bulb with app 2 that takes input from a light sensor, since they interact through the medium of light. Third, we can pair apps that control the same global variable. We collect all such pairs in a group called the global variable group. A pair of apps read from or write to the same global variable. In this work, we focus on apps that access the location mode variable. A global variable determines the mode of operation of the smart home, since it is the only global variable that allows apps to perform both read and write operations on the SmartThings platform. This pairing allowed us to find 438 pairs of apps in the device group, 325 pairs of apps in the physical medium group, and 1,081 pairs in the global variable group. It allowed us to focus on a total of only 2,844 pairs of apps instead of blindly forming more than 35,000 pairs from 267 apps in our corpus. Following the three main groups of app pairs, our definition for interaction is that a pair of apps can interact through the same device, same medium, or same global variable. Two apps have a conflict if, when they interact, their interaction may either compromise the correctness of the apps or produce unintended outcome. The fire CO2 alarm and lock it when I leave apps interact as they access the same door lock and conflict when one locks and the other unlocks the door consecutively, compromising the correctness of one another and potentially producing unintended outcome. To guide our research, we also defined 5 research questions, namely what kinds of app interactions, what kinds of conflicts can we find in the pairs, how prevalent are there unsafe coding patterns, and finally, how can we do automated detection? Let's take a look at the first group of pairs, the device group, and let's answer the first question. For the device group, we found 4 types of interactions. First, direct interaction. Let's look into this example. At first, we found an app called Big Turn On, which can turn on switches, and it is controlled manually by the user by pressing a button on the app. Then we realized that 2 users can actually use the Big Turn On app to control the same switch. Since the intent comes directly from the user, we did not label this as a conflict. We consider that they interact. Second, composable interaction. We have looked at the Fire CO2 alarm app that conflicts with the Lock It When I Leave app. To our surprise, we discovered that there is another app called Initial State Event Streamer that monitors device status and streams this information to our website. Although the developers did not coordinate with one another when coding these apps, the Fire CO2 alarm and the Initial State Event Streamer apps are intended to interact and work together, and therefore they're composable. Third, different feature interaction. This category is also interesting. At first, we plainly thought that all app pairs that write to the same device would behave like the Fire CO2 alarm and Lock It When I Leave apps. Namely, they have a conflict when controlling the same door lock. In fact, we discovered that there are a number of pairs in which both apps write to the same device, but they just interact. For example, we found the Keep Me Cozy and Thermostats apps that write to a thermostat. One app controls the heating or cooling feature, while the other controls the thermostat operation mode. Therefore, because they write to different disjoint features of the same device, we consider them interacting and not conflicting with one another. Another interesting category that we found is same feature interaction. We found this pair of apps called Lock It at a specific time and Auto Lock Door that write to the same device, namely the door lock. We again thought that they would have a conflict. To our surprise, actually they both attempt to lock the door lock, and so they interact through the same feature, but they never have a conflict because they always write the same value to the same feature. So, how about the conflicts in this group? For the device group, we first found feature conflicts. As we have seen before, the Fire CO2 alarm and Lock It When I Leave apps attempt to lock and unlock the door lock. They attempt to write to the same door lock and the same feature with different values, and so they have a conflict. Second, saved state conflicts. In this category, we discovered apps that use a local state variable to keep track of the state of a device feature. If one of these apps is paired with another app that also controls the same device, when the device feature changes its state, the first app updates its local state variable, but this value change is not visible from the second app. In one interesting scenario, we found the Thermostat Auto Off and Thermostat Mode Director apps that both control a thermostat. In its operation, the Thermostat Auto Off app saves the state of the thermostat to its local variable, and at a certain time, it can restore the thermostat state back to this saved state. Let's suppose the Thermostat Auto Off app saves the initial state of the thermostat to its local variable. namely when it's initially off. When the thermostat mode director app changes the state of the thermostat to cool, this change is not reflected on the thermostat auto off's local state variable. In the future, this thermostat auto off app would restore the state of the thermostat to a stale value as it has dropped the update from the thermostat mode director app. We call this dropped update. In another scenario, we found a pair of apps called the auto humidity vent and big turn-off apps. They both control the fan. Let's suppose that the auto humidity vent app turns on a fan and stores the fan state in its local state variable. Using the big turn-off app, a user can turn off the fan, but this update will not be captured in the auto humidity vent's local variable. This may cause the auto humidity vents app to stop functioning because it is unaware that the big turn-off app has turned off the fan. The next time the sensor reading indicates that the auto humidity vent has to turn on the fan, it would simply read its local state variable and think that the fan is already on. We call this invalid local state. How prevalent are these conflicts? These conflicts account for nearly 60% of all app pairs in the device group. Are there unsafe coding patterns? Not too surprisingly, among the conflicting pairs of apps, we found the following patterns. First, we found a pattern called blind update. An app performs updates to a device feature without first checking the most up-to-date state of the feature, and saved state, where an app uses a local state variable to keep track of the state of the device feature, and this local state variable is not visible from other apps. In our previous example, checking the current status of the fan can actually help the auto humidity vent app verify that its local state variable is consistent with the actual device state. The next time the sensor reading indicates that the auto humidity vent app has to turn on the fan, it will continue functioning as it checks the actual status and realizes that the fan is actually off. Now let's look at the physical medium group. We found app pairs in which the two apps interact through water. For example, we found an interesting pair of apps called the Sprayer Controller 2 and Close the Valve apps. The Sprayer Controller 2 app schedules irrigation periodically, while the Close the Valve app closes a water valve when the water sensor detects moisture. When the water coming from a water sprayer controlled by the Sprayer Controller 2 app reaches the moisture sensor used by the Close the Valve app, the two apps interact. Second, sound. We found another interesting pair of apps called the Bose Sound Touch Control and InfluxDB Logger apps. While the Bose Sound Touch Control app controls a sound-producing speaker, the InfluxDB Logger app reads from a sound sensor. Therefore, these two apps interact through sound. So how about the kinds of conflicts in the physical medium group? First, water. To our surprise, although the Sprayer Controller 2 and Close the Water Valve apps basically interact through water, they can potentially have a conflict in this way. If the Sprayer Controller 2 app controls a water sprayer whose water source is the water valve controlled by the Close the Valve app, a bad moisture sensor placement could cause the Close the Valve app to close the water valve and prevent the irrigation when the water coming from the Sprayer Controller 2 app reaches the moisture sensor. Similarly, we found apps that conflict through motion. This exciting pair is called the Niato Connect and Forgiving Security apps. The Niato Connect app controls a vacuum cleaning robot, whereas the Forgiving Security app sets the alarm to go off when its motion sensor detects some movement. When the robot is moving around the house for cleaning, its movement could trigger the motion sensor of the Forgiving Security app that subsequently would turn on the security alarm. In this case, it causes a false alarm. And finally, we found app pairs that conflict through light. In this interesting pair that we discovered, if the light bulb controlled by the Turn On at Sunset app is close enough to the illuminance sensor of the Light Up the Night app, this could disturb the operation of the Light Up the Night app, whose sensor is supposed to detect sunlight, not light from a light bulb. Next, how prevalent are these conflicts? These conflicts constitute more than 90% of all app pairs in the physical medium group. Are there unsafe coding patterns? For the physical medium group, we do not find any unsafe coding patterns since we consider it as physical proximity problem, namely the proximity between the actuator of the first app and the sensor of the second app. For the global variable group, we found app pairs that interact when they perform read and write operations on the location mode variable that determines the mode of operation of a smart home. In a way, this has a similar effect compared to race detection in the traditional concurrency, namely if two apps write different values concurrently to the location mode variable, we have a conflict. Nevertheless, it has its own twists and turns in the context of smart home environment. I highly encourage you to find more detail about this in our paper. Now we finally arrive at the fifth research question. How can we automate the conflict detection? The manual study we first conducted gave us the following insight. We found that for the device and global variable groups, more formally we can say that two apps conflict if we can find two actions that are performed consecutively and they both update the same device feature or variable with different values and the final action is not controlled by the user. Based on this insight, we created our automated detection tool called IoT-Check. IoT-Check is based on model checking to execute a pair of apps exhaustively so that the execution trace would contain the two actions that cause a conflict according to the definition. Learning from the existing work, we also run the actual apps without any translation because translation can cause loss of expressiveness. We created IoT-Check as a simulation framework that mimics the operation of the actual SmartThings platform. Instead of using actual device handlers that control actual devices, IoT-Check uses virtual handlers. A virtual handler controls a state variable that represents the state of an actual device or the location mode variable. On top of that, as a model checker, we extended an existing stateful model checker called Java Pathfinder or JPF to run code written in Groovy, a JVM-based language in which the smart home apps are written. This extension involves extracting away all of the internal Groovy states that do not pertain to the app states. With IoT-Check, we can run a pair of apps that have been pre-processed and pre-configured on the simulation framework. As the apps are running, the model checker controls and generates events such as sensor events that trigger the apps to explore different execution paths. When the execution path contains instructions that perform updates to a device feature or to location mode, they will update the state variable in the virtual handler. At the same time, the model checker is also listening to these updates, and upon finding two conflicting updates to the same state variable in the same virtual handler, it stops the execution and reports the conflict. The main challenge here is that we may have a path with a conflict, but this path is not explored in one JPF execution. For example, consider this execution that has a transition in which app 1 locks the door lock and another execution that has a transition in which app 2 unlocks the door lock. These two conflicting transitions are explored in different executions, and so to address this, IoT-Check's conflict analysis uses the standard data flow compiler analysis that explores the execution graph, in which nodes represent execution states and edges represent transitions that may contain updates to a device feature or a global variable. With this approach, the graph is constructed as a summary of all states and transitions visited and performed in past executions. Although two conflicting transitions are not explored in a single execution by JPF, the graph would capture the two and the analysis will catch the conflict when it sees that there is a path that contains the conflicting transitions. Please find more details about IoT-Check, including information on how to download it. We model checked the app pairs using IoT-Check with the manual study results as ground truth. Overall, we obtained a recall rate of close to 96% for automatic conflict detection in the device and global variable groups. For the physical medium group, IoT-Check prints out warning messages for potential conflicts between a pair of apps. It does not perform model checking for this group because it is a proximity issue, not a coding issue. To conclude this presentation, I presented to you a wide-scale study on smart home apps to better understand how they interact with one another and the problems that may come with these interactions. We found that conflicts are pervasive in smart home apps. Based on the insights we gained from the manual study, we created IoT Check, an automated detection tool based on model checking. Thank you very much for watching and listening to my presentation. Please check out the paper for more details and also the software and dataset release.